Hello and welcome to Add-on. So today we are going to learn about Betatron, a type of particle accelerator that speeds up electrons using a changing magnetic field. Ready to explore how it works, why it's effective, and even take a look at the math behind it. So let's break it down step by step. First things first, the principle of the Betatron. When a charged particle like an electron moves perpendicular to the magnetic field, it experiences a force that makes it curve into a circular path. So here's a question for you. What's the name of this force? Exactly, the Lorentz force. In a betatron, we use this force to make electrons move in circles inside the chamber. But here's the trick. Instead of a steady magnetic field, we keep changing the field strength. So what effect do you think this changing magnetic field has on the electrons? Yes, it accelerates them. This changing magnetic field creates an electromotive force, or what we call EMF, that boosts the electron speed every time it completes a circle. That's the principle behind Betatron. Now let's talk about its construction. So, the Betatron has a magnetic core surrounded by a coil, and this coil is where we pass an alternating current. This setup produces the changing magnetic field needed for acceleration. And in the center, there is a donut shape. It's a donut shaped vacuum chamber where electrons move in a circular path. So, the magnetic field lines go from one pole to the other, passing right through the path of the electron. So, here's a quick question for you. Why do you think the chamber is donut shaped? Good thinking. It's because the circular shape keeps the electron in a fixed path where they are being accelerated. The fields guides them around and around, letting them gain more and more energy with each cycle. Right. Now let's look at how it actually works, starting with the physics of the acceleration. When the magnetic field changes, it creates an electromotive force or EMF in the electron's path. This EMF, which pushes the electrons to higher speed, is given by the formula E equals to d phi by dt, where phi is the magnetic flux and d phi by dt tells us how quickly the flux is changing. So here's a quick question for you. Why does this EMF increase the electron speed? Exactly. The EMF acts as a driving force, giving the electron an extra push as it moves. And the faster the magnetic flux changes, the stronger this push will be, right? So we calculate the work done on the electron in each complete circle as EA equals to negative of E d phi by dt. Here E is the electron's charge and it multiplies with d phi by dt to show how much energy is added with each term, right? Now let's go one step further and figure out the force on the electron. Since force can be described as work done per unit distance, right? We rewrite it as F equals to minus E by 2 pi r d phi by dt, where r is the radius of the orbit. This force is what keeps the electron moving in its path while it's speeding up every time in each cycle. So here is a quick question. Why do you think we divide by 2 pi r? Right. The term gives us the circumference of the electron's circular path, turning the energy per orbit into a force along its path. Now here is where it gets interesting. We know that an electron has a momentum when it's moving. Everything has a momentum when it's moving. For an electron in a betatron, the magnetic force provides the centripetal force needed to keep it on a stable orbit. So we say that dEV, which is a momentum, is given by dEV equals to mv square by r, where B is the magnetic field, E is the charge, V is the electron speed, and m is its mass. Now, after rearranging, we have V equals to PER by m. Now, if we substitute the speed into the formula of the momentum, we have P equals to mv equals to BER. And by this expression, it shows us that the electron's momentum depends directly on the strength of the magnetic field and the radius of the orbit, right? So here's another question for you. Why is it useful to know this momentum? Why do we need to know it? Exactly, knowing the momentum helps us calculate the forces involved and keeps the electron's orbit stable. And speaking of stability, here's the most important part. Considering the orbit to be of fixed radius, then r equals to 0, so we have F equals to ER dB by dt. Equating both the equations of F, we have ER dB by dt equals to E by 2 pi r d phi by dt. Now d phi is equals to 2 pi r square dB. On integrating both sides, we have integration from 0 to b, we have after integrating 2 pi r square, integration of 0 to b dv, we have the magnetic flux equals to 2 pi r square b. Now, to make sure that the electron does not spiral out, the betatron has to follow a special rule. The magnetic flux through the orbit needs to be twice the flux from a uniform magnetic field. And we can write it as phi equals to 2 pi r square b. This condition keeps the electron's path stable by balancing the forces acting on it, ensuring that it stays smooth in a circular orbit. Right? Why do you think this double flux rule is important? Why do you think? Right. It's essential because it keeps the orbit's radius constant, preventing the electron from drifting. And here's a fun fact. This flux condition is why the betatron only accelerates during the first quarter of each magnetic field cycle. The electron is injected when the field is low and taken out when the field reaches its peak, which keeps this process efficient. Right. Now, to sum it up, we have the betatron. The betatron accelerates electrons using a changing magnetic field in a donut-shaped chamber. By controlling the field, we keep the electrons in a stable orbit while steadily increasing their speed. It's a fascinating machine, right? And it's precise engineering that allows for high-speed electron acceleration. Now, thanks for following along. I hope you enjoyed this session. If you have any question or want to explore more about particle physics, keep watching the next videos. Thank you.